Welcome students. PCH 4802 Unit 3 1 Group CC disconnection. Today we are going to discuss on regioselectivity. I am Dr. Devang Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. A point to discuss in today's lecture. We'll begin with introduction, in which we're going to discuss regarding the chemoselectivity and regioselectivity and difference between chemoselectivity and regioselectivity with certain example. Then we are going to discuss the regioselective alkylation of ketone and the problem arising in the regioselective alkylation of ketone. Then we will going to discuss regioselectivity in nucleophilic addition to enone. And finally, we're going to discuss the carbon nucleophiles in conjugate addition and compare one to direct addition with conjugate addition, that is Michael addition. Well, chemoselectivity is how to react one functional group rather than the other. If a compound have more than two functional group and one is more reactive functional group and other is less reactive functional group, and if you want to react with a less reactive functional group, then it will be little bit difficult. There we can use chemoselectivity, and therefore chemoselectivity is how to react one functional group rather than the other. That is known as chemoselectivity. Now we must face a more suitable and demanding problem, and that suitable demanding problem is how to react one specific part of a single functional group and no other. It means even in the functional group there should be more than two elements. Then with one specific part of that functional group, if we want to react with, then instead of chemoselectivity we need to use regioselectivity. That means regioselectivity is nothing else but it is the technique how to react one specific part of a single functional group and no other. We have already seen that the anions of phenols, like these phenoxide anions, are like alkylated at oxygen to give ethers, like we got in structure 3. While enolate anions, that is this enolate anion, are alkylated at carbon to form a new carbon-carbon bond, that is in the 6th structure. So that is called a regioselectivity. Now to explain more in regioselectivity, we have this unsymmetrical ketonic group, carbonyl group, and we are going to treat it with methyl iodide. Then if the methyl group is going to attach on this side of the carbon, it gives a structure 7, and if it attach with the either side of this carbonyl group, then we're going to get structure 9. Similarly, if we have enone kind of compound and we treat it with any nucleophiles, then the nucleophile, if going to attack on the carbon of the carbonyl group, then we're going to get this structure 12. And if the nucleophile is going to attach on the conjugate side, that is in this double bond, then that addition reaction will going to give us structure 10. So to learn more into that, by and large in those two cases, what you get is what you want. We shall look at two important aspects of regioselectivity where we may want either results. We should like to be able to alkylate unsymmetrical ketone, that is structure 8, on one side or another to give structure 7 or 9, which already we have seen in the previous slide. We should like to add nucleophiles to enones either directly at the carbonyl group or which gives 12 structure, or in conjugate fashion to give structure 10, which already we have seen in this case. The unsymmetrical carbonyl group, if the methyl group attached on either side of the carbonyl group, this structure 7 or 9 is going to be obtained, and for this enone, if the nucleophile is going to attach on the carbonyl carbon, it gives structure 12, and if at conjugate side, then we're going to get structure 10. So that is Regioselectivity activity. Generally, we use two specific enol equivalents for alkylation reaction, that is lithium enolates and 1,3-dicarbonyl compound. These are the reagents which required for the alkylation of enol. Both will help us to solve the regioselectivity issue in the alkylation of unsymmetrical ketone. Suppose we want to make structure 13, this one. At first sight, it appears that we must alkylate unsymmetrical ketone, this unsymmetrical ketone, on the more substituted or more branch would be there, that side it should be alkylated. But if sorry if we remove the benzyl group and add our activating ester group instead of this benzyl group, removing or disconnecting this benzyl group, we will going to add more activating ester group to give the structure 14. It is clear that we can make this by another alkylation, and the activating group will promote both cases. Here it is the disconnection given for this target molecule, that is structure 13. Carbonyl carbon is carbon number 1, this is carbon number 2, and after carbon number 2 we have put this wiggly line. So we have put a disconnection, that is a kind of 1,2-CC1 group disconnection, which going to gives us two synthetic equivalent. One is benzyl bromide and the other one is this ester group. And in this ester group also, this carbonyl carbon is carbon number 1, this is carbon number 2, and after carbon number 2 we put wiggly line. It means this disconnection is also 1,2-CC1 group disconnection, and it's going to gives us this ester compound with propyl bromide as a synthetic equivalent. Now after that disconnection, we need to study the synthesis. So benzyl is the more reactive bromide, so it makes sense to add it last, since making the quaternary carbon will be difficult. So this is how we can solve the regioselectivity issue, by adding benzyl. Because of its more reactivity, benzyl bromide we are going to add it last, so that it's going to make quaternary carbon, which is little bit difficult to synthesize. This was the order followed in the published synthesis, and this is the synthesis of the target molecule. We have started with the acetate compound, ethoxysodium. We'll treat that one first and followed by propyl bromide. So we're going to get the side chain over here. So that side chain is going to be obtained in the structure 14. That structure 14 is all again treated with this ethoxysodium followed by benzyl bromide. So we're going to get another benzyl bromide chain over here. That is structure 15, which is base hydrolyzed first, treated, followed by the acidic treatment. It will going to gives us target molecule. If we had wanted the isomeric ketone, that is structure 19, this isomeric ketone if we want to synthesize with the benzyl group benzyl bromide on the other side of the carbonyl compound, we could use a property of lithium enolate. We have kept secret until now. Enolate formation with LDA goes on the less hindered alkyl side chain, particularly if it is a methyl group. We could start with acetones, that is structure number 16, alkylate on one side. So one side is going to be alkylated by treating with LDA followed by propyl bromide. We are going to alkylate it from this carbon. So we are going to get this chain over here, side chain is going to be obtained, and structure 17 is going to be obtained, and then treat it with the LDA. So treat it with LDA. Now kinetically selective selectivity gives the lithium enolate. That lithium enolate structure, kinetically selectivity is going to give us this lithium enolate. We will not going to isolate it and then treated it with the benzyl bromide. That means we are going to benzylate it and it going to gives us structure 19, which is isomeric ketone. This looks very clean, but a careful study of the closely related ketone, that is structure 20, shows that the ratio of less substituted 21, that is less substituted 21 this side, to more substituted enolate 23, that is more substituted that side, double bond is shifted enolate 23. The ratio between these two is 87, this one 21, then 30 would be 23, that is 87 raised to 13. So the product 22 is going to be obtained, inevitably contaminated with a 24. So this product is going to be obtained with the contamination of this 24 in little amount. Regioselectivity is better when the contrast is between secondary and tertiary center, as with cyclic ketone 25. The less substituted lithium enolate, this one, is formed almost exclusively 99 raised to 1. So less contamination and very pure compound 27 is going to be observed after the benzylation. It is, however, possible to make such compound in good yield from 1,3-dicarbonyl starting material. Another isomer of 13 and 19 is the branched ketone, that is 28. That is also isomeric form. Disconnecting by a method, we can use the acid derivative, that is 29, which could be made from manolate, that is structure 31, by 2 alkylation via 30. So first we're going to get this target molecule. This is a disconnection approach or disconnection or retrosynthetic analysis. We have taken this carbonyl carbon compound, isomeric dicarbonyl starting material. To get that, we'll take this 28 structure. The carbonyl carbon is number 1. After that number 1, this is a branched ketone. So after that number 1, we put wiggly line. So this is a kind of 1,1-CC 1 group disconnection. So that is the method, that disconnecting from 1,1-CC 1 group disconnection, we're going to get this synthetic equivalent chloride. Then we're going to perform FGI, functional group interconversion. So chloride is converted into more active acetate group. That acetate group contain carbonyl carbon, and that carbon is number 1, and after that carbon, this is number 2 carbon. So after number 2 carbon, we are going to put 2 wiggly line over here. One is this one, the other one is this one. So this is a 1,2-CC 1 group disconnection, and it's going to gives us a malonate structure, that is 31. Now the synthesis over here. The published synthesis uses a cadmium reagent, but we should rather use copper nowadays. Double alkylation of manolate, that is structure 31. Again adding the benzyl group last, that is 33. We are going to add benzyl group over here. Hydrolysis and decarboxylation, these two process releases the free acid. That free acid 34 is going to be obtained, which is easily converted into its acid chloride. It can be converted in acid chloride by thionyl chloride followed by propyl cadmium, or perhaps beta dipropyl lithium cuprate into the target molecule 28 is going to be obtained. So this is the synthesis. We have taken this compound 31, then it is treated with ethoxy sodium followed by methyl iodide. So that compound get alkylated at this position, carbon position will get the alkylated product of malonate. Alkylated malonate further treated with ethoxy sodium followed by benzyl bromide. So another branch is going to be obtained, that is benzyl bromide attached to this gives structure 33, that is base hydrolyzed, and after decarboxylation we're going to get this free acid, and that free acid is further treated with thionyl chloride followed by dipropyl cadmium or either dipropyl lithium cuprate. It's going to give you target molecule. Next, that is another problem of getting direct 1,2 or conjugate 1,4, that is called Michael addition to alpha beta unsaturated compound such as enone, that is structure 11, can be solved without finding abstruse strategy by choosing of a reagent. So the regioselectivity gives another solution for this, either 1,2, that is a direct addition of the nucleophiles and give the structure 12, or either conjugate addition to give structure 10. For that we have certain general principles. Among them, the number 1 is the conjugate addition product 10 is thermodynamically favored as the weak double bond been lost but the strong double bond retained. The direct addition product, that 12 product 12 is kinetically favored. Direct addition is more easily reversed than conjugate addition. So the more stable the nucleophile, the more reversible 1,2 addition will become and more 1,4 addition predominates. The third point, the site is the harder and the site of conjugate addition the softer nucleophilic site. So more basic nucleophile try to make 1,4 addition and less basic nucleophile try to prefer 1,4 addition. We saw that the more electrophilic alpha beta unsaturated compound, the more likely it is to do direct addition. If more electrophilic nature is there of the alpha beta unsaturated compound, the more likely is to get direct, that is 1,2 addition with heteroatoms, and some same is true for the carbon nucleophiles as well. Grignard reagent normally add direct to alpha beta unsaturated aldehyde such as structure 35, where you can see direct addition is there and it gives 85 to 90% yield of structure 36. Sorry, may add in conjugate fashion to alpha beta unsaturated ethers, particularly if they have a large esterifying group such as tertiary butyl group like we have in structure 37. Then this Grignard reagent will going to gives us direct 1,2 addition, conjugate addition, sorry, 1,4 addition, Michael addition will going to get 60% yield for that. Among nucleophiles, we saw that the softer, less basic nucleophiles such as sulfur are good at conjugate addition, that is Michael addition. Hydride reducing agent and alkoxide are better at direct addition, that is 1,2 addition, while amines are somewhere in the middle. They may give either 1,2 or 1,4 addition depending on the nature of the compound. This means that alpha beta unsaturated aldehyde, ketone and ester may all be reduced at the carbonyl group with sodium borohydride for aldehyde and ketones, or lithium aluminum hydride for esters, is as shown in the example 14. That is ester, we need to take reducing agent as lithium aluminum hydride to get our structure 39. Catalytic hydrogenation, however, not an ionic reaction. Catalytic hydrogenation simply reduce weak bonds such as carbon double bond carbon or carbon double bond oxygen and going to give us structure 41. Now an example is the preparation of unsaturated alcohol, that is structure 12, this is unsaturated alcohol, we're going to perform functional group interconversion. It's going to give us, instead of hydroxyl group, more more active ester group is added instead of hydroxyl group. And when you reach to this target molecule by reduction, that is lithium aluminum hydride, you are going to get your target molecule 42. 85% yield is going to be obtained, and that structure 42 is going to be obtained, whose benzyl ether was needed for Diels-Alder reaction. Reduction of this diester 43 with lithium aluminum hydride gives 85% of the yield in a unsaturated alcohol. Now next topic is about carbon nucleophiles in conjugate addition. The very basic and aggressive nucleophilic organolithium tend to do direct addition to all alpha beta unsaturated carbonyl compounds. The rather less basic Grignard reagent may add in ether sense, as we saw for a compound 35 and 37. We know how copper in first monooxidation state is the key to pursuing either alkyl lithium, I is missing over here, or Grignard reagent to add in conjugate fashion. If we react 11 with a Grignard reagent with copper 1 or monovalent copper catalysis, we get 44 as the product. This one with Grignard reagent and cuprous bromide will going to give us 44 product. With alkyl cuprate, the initial product is actually the lithium enolate that we're going to obtain, and that lithium enolate is going to attacked by electrophiles to give structure 46. Of course, if the nucleophile is a proton, the product is still going to be 44. That you need to note down. As we know, addition of the cuprate to a cyclic enon such as 47 followed by tapping with an electrophile gives anti-stereochemistry, that is 48. So we have this kind of enon, that is 47 cyclic enon, and we are going to treat it with allyl lithium cuprate followed by alkyl bromide. We're going to get this stereochemistry 48. So when a chemist at Dortmund wished to make the syn compound 49, they chose to add diallyl lithium cuprate to enon 50 with one side chain already in place. This gave the lithium enolate 51, and protonation gave the syn compound, that is 49. The choice of acid was important. Phenol were good and 52 was the best. This one is very best compound to use here to form this compound 49. Thermodynamic control dominates when a cis ring junction is preferred as between the flat 5-membered and the flat 6-membered ring in structure 55. This 100% is going to be obtained. A reversible protonation of lithium enolate, that is 54, occurs on the same phase as the methyl group on the exo phase. The molecule prefers a folded conformation. Stereochemistry may be created during an addition step, as in the formation of 57, 98% yield, and 59, 100% yield. Cuprate addition to 56 gives 12, a 98 raised to 2 ratio of anti-enzyme products 57. While the addition of phenyl cuprate in presence of acid prepared from phenyl lithium or cuprous iodide and perhaps diphenyl lithium cuprate to 58 gives 13A, that is this one, and 96:4 anti-enzyme ratio in of structure 59. In both cases, the cuprate has added from the opposite phase to the substituent, but the stereochemistry of 57 is probably dominated by axial attack giving a chair product, while 59 has both substituents at equatorial position. But most of the time we are chiefly concerned with the getting the carbon nucleophile to add 1,4, that is Michael addition. The synthesis of the unsaturated ketone 62 makes 2 more points. While we cannot do SN2 reaction on vinyl halide, they make good organolithium and copper reagents, and in addition to cyclohexane, propenyl bromide both forms the courage and adds with retention at the alkene. Well, thank you for paying attention to this video lecture. I hope you like this, and if you have any question or doubt, you can ask a question or you can email me, because as you know, asking that asking question is a beautiful way to gain knowledge.